I'm super excited to be here in GopherCon. It's my first time here in GopherCon in general. And thank you for taking time to join me in this talk today. We will be going to talk about how not to write a test in Go. So let's outline the agenda for today. I prepared this talk in hope that everyone, regardless of their experience level, will take away something new. We'll start with a brief overview of why testing is significant in general, and we'll then revisit some of the basic concepts of testing in Go. We'll continue with exploring some common practices and pitfalls that can set back your testing efforts. My name is Amir. I work as a software engineer at Armo. I'm very picky about my coffee, and you guessed it right. I'm glad to be here in London today. And one of the things I also do is that I'm a maintainer of Kubescape. So a few words about Kubescape. Kubescape was created by Armo. It's an open source Kubernetes security platform which helps you find misconfigurations and vulnerabilities within your clusters. Kubescape is part of CNCF. It's written in Go, and we are always glad to have new developers join our growing contributor community. So that's about Kubescape. You're probably telling yourself, I know how not to write a test in Go. I simply don't write one. That's what my manager told me when he read the title of this talk. So that's true, but so let's take a look at this graph. Most of this talk, we're going to see code blocks, but I feel like there is no tech talk without a graph, so I chose this for a good reason. We're all familiar with this graph. It's the software development lifecycle. So the cycle starts in coding, then we test our code through unit testing, integration tests, system tests, until we finally release it and it gets delivered to the end user. So we see that detecting bugs in the early stage will cost us much less to fix them. And also, most of the bugs will be discovered while we write our code and while we write unit tests. So let's start with the most important question: why should we test our code? So first, we would like to find bugs. Find bugs during development. And it also increases our trust and confidence in what we are doing, and it helps us to make sure that we didn't break anything. And in Go, we also have something called benchmarks. So benchmarks helps us to measure the performance of our code. And I feel like the most important point of unit testing is also documentation. By reading unit test, we understand what was the developer's intention through test cases. So let's start with the basics. So what is a unit test? So it would usually test a function or a set of functions, and it will compare the actual behavior versus the expected behavior. And while doing so, it should run in complete isolation. That means we will not typically connect to any external dependencies, such as databases or HTTP services. And this will allow our unit tests to be fast and stable, so that they won't fail due to problems with those external services. What unit tests don't do is that they can't prevent bugs. They can only help us identify them early in the cycle. And unit tests alone can't validate the entire application. For that, we have the integration test or the system tests. And also, it's very much impractical to test every possible test case. Usually, with unit tests, they are designed to test expected inputs and some edge cases. So let's dive into the basics of unit testing. So obviously, Go didn't invent unit testing, and a general structure for unit test would follow these 3 steps. First, we will set up the test data. Then we will call the function or method that we are testing. And finally, we will assert that the result is according to what I expect. So let's say we have this add function that we would like to test. It receives to integer and returns the result, an integer. So we'll start off by creating a file which matches the same name as the file of my add function. In this case, it will be add_test. And as of the name of the package, I get to choose. So there is something called black box testing, sorry. So black box testing allows me to check only and to test only the external behavior of the package that I'm testing. So in this case, it's a separate package, and Go allows us to have one extra package under the same directory with the _test suffix. So this is more of a personal preference, so it's really up to you. And then what we'll do is we will import the Go testing package, and our test function will be called test_add, and the parameter will be testing.t. So then we will call the function with the input, and then we will assert on that output. That's great. So this is how you run a simple test. You run the go test command with your test file. And another thing is that any fixtures could be any JSON files that I may need to run my tests, would be placed in a special directory called the test data. The compiler knows to ignore anything that we place there. So as for function naming conventions in Go, if we're testing a function, hello world, obviously the name of the test function would be test hello world. And if it's a target method of a struct, so it will, in this case, we have the bar method. So the function, the test function would be called test, the name of the struct, underscore the name of the method. So we got the basics out of our way. Let's try to make some improvements to our tests. So this is an example of how not to write a test. So I have the simple function that we saw earlier, and I have on the right a code that checks separate test cases with different input values. So we can clearly see that we have some code duplication in here. So we call the function that we are testing 3 times. We check the result. And by reading this code, I'm not very sure what I'm checking here. I can assume that I'm checking maybe 2 and 3 because it's an edge case and a negative and a positive. And maybe I don't know why I checked zeros, for example. So let's see how we can improve this test. And this brings me to the first topic, which is structured tests. So there is something called table-driven tests. So what a table-driven test is, usually we'll have a struct with the name of the test, some inputs, and the expected output. So each element of this slice will be a test case. So in this case, we see that we check for positive numbers, and then we are checking for negative and positive, and we think that zeros also worth checking. And what we will do next is we will place all our test logic in a loop, which will loop over each of these test cases, and we'll call the trun, and trun actually create subtests for us. So it's with this approach, what happens is that it makes our unit testing more structured. It makes it easy to add different test cases. I simply add an element to this slice, and obviously it reduces code duplication. And this is how the output looks like. I can see each of my test cases separately, and I can also run a specific test case. And this is something I couldn't have done using a single function. So what if I told you we can run a test faster? So some of you may be familiar with the parallel function. The parallel function actually signals the test to be run in parallel with other parallel tests. Placing the parallel function is as easy as calling t.parallel, and it also allowed to be placed inside our subtests. So it's good for speeding up long-running tests, and it's parallel at the package level. So how it works is that all my sequential tests are completed, then Go will run all my parallel tests. However, let me tell you something. This will not work. So if you go back to the code, we can add some log print, in this case running the name of the test case, and let's look at the output. So for some reason, we see that we called the add zeros 3 times. And I think one of the worst things that could happen is that all my tests passed. So what happened here? Anyone has a clue? Very nice. Right. So this is something called the loop variable in Go. So it's a well-known Go gotcha. So in our case, what happened is that we used the TC variable, which is the loop variable, and we sent it, we used it in the closure function. So what actually happened is that by the time the Go routine starts, because we were using the T parallel, so the TC variable got evaluated, and I ended up using the same value for all my test cases. So it's pretty easy to fix this thing. I would simply declare a local variable inside the loop, and this will create a copy of it so that the Go routine will now use this locally scoped variable. Note that in Go 122, the Go team is considering on changing the semantics of the loop variable, so you can keep an eye on that. And this is how the output looks like once I run my fixed code. So the next topic, which is also related to structured tests, is test suites. So a test suite is a set of test cases. Usually we would like to group tests by maybe a functional test, and we have performance tests. So you would probably ask yourself, why not always use table-driven tests? So especially, we have some scenarios with a complex setup and teardown, and this is where test suites are very good for. So let's look at the execution process of a test suite. It would usually involve a setup when we prepare the environment for testing. Then we will execute each of our test cases. This might or might not involve a setup or a cleanup phase. And finally, we have a global cleanup. So Go provides something called the testing M type. So using the testing M type provides us with a global setup and teardown at the package level. And there's no better example than looking at code. So in order to use it, I need to define a function called test main in my package. And there could be only one function in a package with the same name. And by calling the mrun, all my tests in that package will run. So what I'm able to do in this approach, I'm able to provide some setup and teardown code before and after this call. So this is one approach. And there are some external libraries that can be used for unit test that I mentioned here. But in general, the standard testing package of Go should cover like most of the use cases for you, I'm assuming. So I would like to focus on the testify package because it does provide something for test suites. So it will be called suite from testify package, and it will provide more control over the setup and teardown. It will come also with some rich set of assertions so you can use. And there are some built-in functions when you use the testify package. So we have the setup suite and the teardown suite that they will be run before and after all our test cases. And we have the setup test and the teardown test before each test case. So If you just need a global setup and teardown without additional features, so using the testing would be enough for you. And if you're looking for more structured test suites, so I would recommend to use Testify. And sometimes we just need a simple cleanup for a specific test. So in this example, our test is creating a temp directory. And in the end, it tries to remove this directory using the defer function. So a better approach in this case would not be to use a defer if we're testing. There is something called the cleanup. And cleanup actually receives a function. And we can see it's pretty easy to replace defer with the cleanup. And it receives a function, and we'll replace the OS remove all. So what is the advantages of using the cleanup? So as I said, it registers a function, and it will be called when the test or subtests are completed. And it will be called in a LIFO order, similar to the defer function, but it will also work in the event of panic. And this is, I find it like more of an improved version of the defer. So this is the part where you feel you did something right. And that brings me to the next topic, test categorization. So why do we need to categorize tests? So sometimes we may have long-running tests, sometimes we might have integration tests, or we might not want to run all our tests during CI, or at least at different parts of the CI. So there are two approaches that I'm going to talk about. One is using build tags, and the other one is using environment variables. So with build tags, it's pretty easy. Let's say this is an integration test. I would simply, at the header of my Go file, I will write the tag that I chose, in this case, integration. And once I run the go test command, I simply pass it with this build tag, and it will know whether to run or not to run this test file. Another approach would be to use environment variables. So when I'm using environment variables, I find this approach better because when I use environment variable, I will have to call the tskip function. And this provides me with a way of knowing that I specifically skipped a test. So it's good for, it's good for you to know if you intentionally skipped a test or not. And this is why I find this approach a better one than using build tags. So what do you think is wrong with the following code? Anyone? Okay. So it's called a data race. So a data race occurs when two Go routines try to access the same variable concurrently, and at least one of them is trying to write to that variable. So in this case, we have the I variable, and we have two Go routines trying to change it. Thankfully, Go provides a data race detector, which runs at runtime. And how we enable it, we simply use the -race on the go test command. But note that it can only be as good as our test. It means that it may actually miss some data races. So it's kind of, I would say, enable it if you can. and because the way it works is that when we're enabling this race detector, it actually adds instrumentation to our code. So what will happen is that it will track the behavior of us accessing the memory. So it has impact on memory and performance when we use this flag, because we can use it also with the go build command. So I would recommend to enable it for our testing purposes and not for production code, for example. That's my opinion. And we can also exclude the race detection with the race build tag. Another thing that I would recommend for testing concurrent code is use the count flag. Many times I was able to catch data races only once I increased the count of running the tests. So that's like a nice thing. And this is how the output would look like once the data race is detected. And the next topic, mocks. So what is a mock? Let's clear that off the table. So the broadest definition of a mock, sometimes called a fake, a stub, or a spy, is by substituting a code for a unit test. I don't really distinguish between the three. I find it that they serve the same purpose. And why should we use mock? Because we want to keep the test reliable, self-contained, and fast. So there are several techniques we can use when it comes to mocking in Go. So I find it easy to learn by the situation. So let's have a look at each one of them. So let's say I need to mock a function. In this case, I have the OpenDB function, which receives a set of strings, and it calls the SQL open. So obviously, in my test, I wouldn't want to call the SQL open. So what I can do is something called higher order functions. I will declare an SQL opener type, which is a function which receives 2 strings and return the SQL DB pointer and an error. And I will replace or add an additional parameter to the OpenDB function. And using that approach, what I can do is when I write my tests, I can simply provide a mock implementation for the SQL opener. So another situation is where we need to mock a method on a concrete type. So let's say I have the file data reader, which has a method called readData, which returns a string. And we have the function that we would like to test, which is called the process data. The process data receives a file data reader, and it calls the readData method. So in this case, what we can do is we can replace the actual type with an interface that describes the behavior of that type. So we have defined a new interface called data reader, which has a readData function, which returns a string. And we replace the parameter to the process data function. And for my test, I will provide a mock implementation for that interface. So, and sometimes we will have sometimes a large interface, and we would like to mock a small subset of functions in that interface. So in this case, I have the data reader interface, I have the readData, and another function called writeData. And I would like to mock the readData only. So what I can do is I can declare a new type, in this case, data reader mock, which implements this interface by writing it like this. This is something called embedding, interface embedding. And that means that this type satisfies the interface for Go. So then I will declare the method on that type. But there is a small catch here. Because if my code will call the writeData function, it will panic. So when using this approach, you need to be very careful of which methods your code that you're testing is calling on that interface. So that's a small thing that you need to consider. And there are some good libraries out there that you can use that can help you reduce some boilerplate code. But Go provides also built-in utilities for tests. We have the HTTP test and the IO test. They are part of the standard library, and they provide utilities for mocking HTTP clients and servers, HTTP calls, and some IO functionalities if, let's say, I want to simulate some read or write error, timeout errors, and so forth. So the next topic, randomizing text execution. Why do we need to randomize test execution? Because it can help us ensure that our tests are truly isolated, and it will increase our chance of uncovering bugs. So Go provides with a way of shuffling the test order. It's called the shuffle flag, and it's turned off by default. So you simply enable it by running the go test -shuffle on. And what happens is that when I use the verbose flag on this run, I can see some value. And this is a seed value that will be assigned for each random test that is executed. And why is that important? Because let's say my test failed on a remote server and I would like to reproduce it. So what I would do is I will copy the seed value and I can force the go test command with this seed value with the same shuffle argument. And this will make sure that my test runs in the same order. So that brings me to the last, no, not the last, the next topic for today's talk, benchmarks. Why do we need benchmarks? So with unit tests, we verify that our code functioned as intended, but benchmarks are essential because they help us also check how well and efficient our code performs. So in Go, the skeleton of a benchmark looks like this. We have a function that we would like to benchmark called foo. So the benchmark, the function name which runs the benchmark will be called benchmark foo. And note that we will be using the testing B type in this case. So what we will usually do is we will place the method that we are benchmarking in a loop that is bounded by the n variable. So this capital N is the variable number of iterations, and it will be increased to match the benchmark time. So the default benchmark time in Go is set to 1 second by default, and it can be increased using the bench time flag. So Go will actually try to run this foo function as many times as possible until it reaches the benchmark time. So a benchmark will be written in a test _test Go file and will be executed very much similar to the unit test using Go test. And we can also provide it with it's excluded by default. So in order to run benchmark, we need to use the bench flag. And it takes also a regex if we want to filter some benchmarks. So as for the output, so I can see once I run a benchmark, I can see that this function was executed 29,000 times, and this is like the average execution time in nanosecond. So it doesn't tell me a lot. So usually benchmarking will be used as compared to other benchmarks. Sometimes I have implementation A or implementation B, and I would like to compare the two, because alone doesn't serve anything. I don't know if it's fast or not. And one common trap with benchmarks is not resetting the timer. So we might have, as part of the benchmark function, we might have expensive setups which take maybe memory and also CPU time. So just remember to call reset timer, because this will actually reset all the counters of memory and benchmark time and CPU. And Go is a garbage collected language, so we also need some memory benchmarks. So for memory benchmarks, we simply use the benchmem flag, and this will give us some more information on the number of bytes, for example, that were allocated and the amount of allocations per run. So some ground rules around benchmarks. So you must have a stable environment to run your benchmarks. Usually you don't profile on shared hardware, for example. And also don't make wrong assumptions about micro benchmarks. And that means that similar to law of large numbers, if we run a benchmark a large number of times, it should tend to approach its expected value. So what we can do is we can increase the benchmark time, for example. We have the bench time flag for that. And use the count flag to repeat benchmark executions. As for comparing benchmarks, we can use the bench stat tool to compare different benchmark executions. And that brings me to the last topic of this talk, test automation. So I don't know how many of you are responsible for writing CI/CD pipelines or test automations. So I just want to show you how easy it is to automate your testing process. And for the example, I chose to use Github Actions. There's not going to be any demo, so we're just going to see some YAML file. So how we start, if our repository is on GitHub, we can use Github Actions, and we will simply create a directory named .github/workflows, and this is where we will place our push workflow. And this is how the YAML looks like. So first, we will name it build and test, and then we have the triggers. So I want to run it on every push to my main branch. Second, I will choose the name of the runner. In this case, I'm running it on a Linux, and the version of Go that I would like to set up. So, like, if I'm scrolling down on that file, I will have the checkout function, and then I simply call the Go build and the Go test. It's as simple as that. So that's for the short example of how to run your test on every push. So if I try to sum up everything, please try to sabotage with your tests. It's always good to challenge your tests and see if they're reliable. So let's say you change a critical functionality and your tests still pass. You need to rethink about your testing processes. Another point that we didn't talk about is test-driven development. Get familiar with it. It helps you think of cases before you start coding and prevent some potential design errors. And I find this point very personal because I literally practice it every time. Every time that there is a bug, I would usually start with writing a test and have this test fail. And once I fix the bug, I expect this test to pass, and then in this way I ensure that I don't encounter this bug in the future. So this is like a very good point for me. And while I don't really believe in 100% coverage, you can check for code coverage. So Go built-in provides you with a way of measuring the coverage of your code. I didn't cover it in this presentation, but do use it because it will help you understand where you stand in terms of your testing of your project, and like if you maybe missed some critical functionality without testing. And when we come usually to a project without unit test, I would usually start with the pure functions, those functions that don't have any side effects. These are like the simplest ones to start with. And be careful when you mock, because we should mock only external dependencies. So that's like an important point. And do run tests on every push, because when you integrate tests in your CI, you really make sure that you didn't break anything. So that's like my last point for this talk. I think we finished a little bit earlier. So in any case, thank you, and we'll have more time for questions.